The Platonic solids have fascinated mathematicians for centuries. They demonstrate the concepts of regularity and symmetry and extend several properties of two-dimensional figures to three dimensions. Through the visual geometry project materials, we hope to make it easier for teachers to incorporate the study of three-dimensional objects into their geometry curriculum, and to encourage students to investigate questions about polygons and polyhedra. A computer-animated videotape entitled The Platonic Solids shows geometric relationships in three dimensions which are difficult to visualize from drawings alone. Workbook activities allow students to investigate these and other relationships by building and manipulating three-dimensional models. Separate die-cut nets for all the models are also available. Finally, the teacher's edition of the workbook gives suggestions for how to use the materials in the classroom, comments and answers for the workbook activities, additional information about the solids, and black line masters for all the nets. To benefit from the materials, students don't need to know anything more advanced than the concept of a regular polygon. Each activity is designed to take one class period or less. The collection of activities on the Platonic solids can provide a standalone unit, or individual activities can be used to supplement the standard curriculum. The workbook begins with preliminary activities about polygons, investigations on regularity, symmetry, and tessellations in two dimensions. These concepts are extended to three dimensions, beginning with the definition of a regular polyhedron. A regular polyhedron is a closed, three-dimensional shape formed by regular polygons. Its faces are congruent, and the same number of faces meet at each vertex in exactly the same way. By connecting the edges of regular polygons to each other with rubber bands, students can discover that there are exactly 5 regular polyhedra. They are named according to the number of faces they have. The regular tetrahedron has 4 triangular faces. The regular hexahedron, or cube, has 6 square faces. The regular octahedron has 8 triangular faces. The regular dodecahedron has 12 pentagonal faces. And the regular icosahedron has 20 triangular faces. The videotape presents a computer-animated demonstration that exactly 5 regular polyhedra exist. Each part of the definition of regularity is necessary. If the faces are not regular polygons, for example, or are not all congruent, then the resulting polyhedron is not regular. If not all the vertices are formed in exactly the same way, then the polyhedron is not regular. The same number of faces could meet at each vertex, and still the polyhedron might not be regular, as we see if we take off the top dome of an icosahedron and replace it upside down. We must require that the same number of faces meet at each vertex in exactly the same way. Euclid discusses the Platonic solids in the last book of the Elements. It has been said that the first 12 books of the Elements are preparation for this final part, in which he concludes that there are only 5 regular solids. His demonstration is the one on which the Platonic solids video and student activities are based. The regular polyhedron were known and worked with long before Plato's time. These 5 polyhedron are called the Platonic solids not because Plato himself discovered them, but because he wrote about them in his dialogue Timaeus. In the 5th century BC, there were 4 elements thought to make up the world. In Timaeus, Plato associated the solids with these elements. The cube, because it is so sturdy, was the earth. The 3 solids with triangular faces represented various degrees of wetness according to their ratios of surface area to volume. The tetrahedron has the largest ratio and was associated with the driest element, fire. The icosahedron has the smallest ratio and was associated with water itself. The octahedron is in the middle and stood for air. It also spins freely when held between the thumb and forefinger and is light and elusive like air itself. The dodecahedron, which is the most difficult to construct and has the largest volume when inscribed in a sphere, was associated with the universe itself. During the Renaissance, a renewed interest in classical studies rejuvenated the study of the Platonic solids. Mathematicians, scientists, and artists such as Leonardo da Vinci and Lucio Pacioli studied the relationships and characteristics of the polyhedra and showed them in paintings and sketches. Astronomer and mathematician Johannes Kepler also studied the properties of regular polyhedra and discussed them at length in his book, Harmony of the Worlds, published in 1619. Kepler was so impressed with the perfection of the Platonic solids that he proposed a theory in which they were inscribed in spheres which represented the orbits of the planets known at that time. Kepler himself later proved this theory was incorrect and discovered the elliptical orbits of planets. Kepler's study of the relationships of the solids to each other pointed to a concept called duality. Duality serves as a way to pair polyhedra so that the roles of vertex and face have been interchanged. For example, the cube and the octahedron are duals of each other. An octahedron can be inscribed in a cube in such a way that each face of the cube corresponds to a vertex of the octahedron, and vice versa. The dodecahedron and the icosahedron are duals. The tetrahedron is its own dual. The enduring interest in the Platonic solids throughout history is due to the perfection of their regularity. This perfection is exhibited in their symmetry. Symmetry is the harmonious repetition of like parts to create a whole. In the Platonic Solids workbook, students investigate the rotation and reflection symmetries of the 5 solids. Rotation symmetry is explored by using straws as the axes of symmetry. For example, the octahedron has rotation axes through opposite vertices. Rotating the octahedron 90 degrees about such an axis makes it appear to be in its original position, even though 4 of its vertices have changed position. After 4 such rotations, it returns to its original orientation. This axis is called a 4-fold rotation axis. Each of the Platonic solids has several different axes of rotation symmetry. Each Platonic solid also has several planes of reflection symmetry that bisect the solid into 2 mirror image halves. Students can see these planes by stretching rubber bands on a plastic model. Here we see several reflection planes of the cube. Students can use mirrors as reflection planes to create the image of each Platonic solid from just a small piece of it. The mirror kaleidoscope is nothing more than 3 mirrors arranged in a corner. The nets for these seeds, as they are called, are provided in the workbook. Students will notice that the symmetries of dual solids are similar. For example, the rotation axes through the vertices of the octahedron are the same as those through the centers of the faces of the cube. Similarly, the reflection planes of the cube are reflection planes of the inscribed dual octahedron. Here are views of the Platonic solids created by turning them so an axis of rotation symmetry is at the center of the view, and then making the solid transparent, leaving just a wireframe model. The Platonics are viewed in turn, looking straight at an edge, a face, and a vertex. Polyhedra can have surprising two-dimensional projections. The views of the Platonic solids suggest some interesting cross-sections. The cross-section of a polyhedron is the polygon that is made when a plane intersects the polyhedron. In the workbook, students can discover these cross-sections by using transparent models and rubber bands. While square cross-sections are certainly expected in a cube, who would guess that you can get a square cross-section of a tetrahedron or a hexagonal cross-section of a cube? There are many ways in which solids can be inscribed in each other. Inscribing duals is one way. Another is by joining certain diagonals of faces. In this way, a regular tetrahedron can be inscribed in a cube. Each edge of the tetrahedron is a diagonal of a face of the cube. Simple ratios relate the volumes of these inscribed and circumscribed figures. For example, the volume of the inscribed tetrahedron is exactly 1/3 the volume of the cube. The volume of the dual octahedron inscribed in the cube is 1/6 the volume of the cube. Concepts of symmetry, duality, inscribed solids, and cross-sections apply to other solids besides the Platonic solids. The workbook also introduces a number of semi-regular and non-regular solids. A polyhedron is not regular if it fails to fill any part of the definition for regular polyhedron. A familiar non-regular polyhedron is the square pyramid. While all the faces are regular polygons, they are not all the same, and the corners are not the same. Most prisms and antiprisms are examples of non-regular polyhedra. A right rectangular prism is formed by two congruent regular polygonal bases which lie in parallel planes and have corresponding edges connected by squares that are perpendicular to the bases. One of the Platonic solids is such a prism, though it is not usually thought of as such: the cube. Other than the cube, such prisms are not regular polyhedra because not all the faces are the same. A less familiar solid is the antiprism. An antiprism has two congruent regular polygonal bases joined by triangles instead of squares. This is a hexagonal antiprism. All antiprisms are non-regular solids except for the octahedron. It has two equilateral triangular bases joined by equilateral triangles. Prisms and antiprisms are examples of polyhedra whose faces are all regular polygons and whose corners are all the same, but which are made up of more than one type of polygon. These are also called semi-regular polyhedra. The cube octahedron is an example of a semi-regular polyhedron. The faces are regular polygons, and 4 faces meet at each vertex in exactly the same way. But there are 2 kinds of faces, squares and triangles, so it is not regular. Another semi-regular solid is the truncated icosahedron, more commonly known as the soccer ball. It is derived from an icosahedron by dividing each edge into thirds, then cutting through these points at each corner. The new solid is made of hexagons and pentagons, and all the corners are the same. The Platonic solids possess an important property called Euler's formula, discovered by Euler in the 1700s. Euler's formula states that in any convex polyhedron, the number of faces plus the number of vertices minus 2 equals the number of edges. This formula works not only for the Platonic solids, but for the non-regular and semi-regular solids, as well as prisms and antiprisms. Explorations into Euler's formula and many of the other topics introduced in the workbook are included in a section called Student Projects, which contains extra investigations for students to pursue independently. The prerequisites for each project are clearly indicated. The projects do not require that the students do all the activities in the workbook first. Most of these projects require that students build their own models. In fact, all of the activities in the workbook involve building and manipulating 3-dimensional models, a great way to develop the students' visual sense of the world around them.